start the nervous system, you already know that how many systems you have in the body. Yeah, and 2 of those 11 systems are called the control systems, right? The nervous and the endocrine. And which one is first acting? The nervous system, right? Acts very fast because it acts by electrical signal transmission. So nervous system is a very important system of your body, and it is a powerful control system, right, of the body. First, we'll talk about the functions of the nervous system. Then we'll talk about the divisions of the nervous system, how we divide the entire nervous system. Then we'll talk about the cells in the neural tissue or nervous tissue. There are 2 types of cells, you already know. Supporting cells are called neuroglia or neuroglial cells, and the main cells are called the neurons. Both are important. So first we will see the neuroglia or neuroglial cells, and then we'll see the neurons, the main cells. Okay, so we'll talk about both. Then we will talk about few other structures very often we see in the nervous system. What are those structures we see very often? We see tracts, nuclei, gray matter, white matter. So I'll explain you what are those structures, what are the tracts, what are the nuclei, what are the white matters and gray matters. Then we'll talk about the reflex and the parts of a reflex arc. Arc is the circuit needed for the reflex. So those are the things we will talk about. First, the function of the nervous system. You know that nervous system is a powerful control system of your body, so it performs many functions, right? Thousands of functions. But for our convenience, we can divide all those functions into 3 groups or 3 types of functions: sensory input, integration, and motor output. So all the functions can be grouped into those 3 types of functions: sensory input, integration, and motor output. Let me give you an example of those functions. Okay. When something hot touches your hand, okay, your skin has receptors. You remember pain, touch, temperature receptors. So when something hot touches your skin, which receptors will get that signal? Temperature receptors, right? Will get that signal, right? And will send the signal where? To the brain. And that is the sensory input. So receptors receive the signal and sends towards the brain, to the brain. And that is called what? That part is called sensory input. So I can tell now that sensory input goes from the receptors to the brain. Is it clear? Receptor to the brain. Then the brain does what? In this case, can you tell me, anybody, what the brain will do when the signal will go to the brain? What kind of interpretation in this case? The brain has to decide what? Before that, it has to decide if it is hot or cold, right? Only brain can does that, right? Not only that, you see, brain quickly decides so many things. Brain decides if it is hot or cold, right? What is that? First thing, what is that, right? Is it hot or cold? If it is hot, is it harmful or it is comfortable hot, right? If it is a little bit hot, you don't need to care. If it is very hot, you have to care, right? So all those things are done by the brain, right? And if the brain decides that it is very hot, can burn your skin, right? Quickly brain will send signal to the muscle to move the hand away. Is it clear? So you see here, brain is doing so many things, right? Interpreting the signal that it receives and sends motor command, right? Command to the, in this case, what? To the muscle to move the hand away. So interpretation, that is the integration, and motor command is sent to the muscle, in this case, via the motor output. That's the motor output. Is it clear? Okay. Now, let me give you another example. You are thirsty. Very thirsty. You are looking for water, right? To drink. So, if you see a glass of water, okay, that picture of glass of water will go from the skin to the brain or eye to the brain? Eye to the brain. So where the receptors are in this case? Inside the eye, right? Skin cannot see. So the visual receptors are in the retina of the eye. Is it clear? Retina of the eye will receive that signal, picture, and send again to the brain. Now you tell me, in this case, if you see a glass of water, you all know the eye sends signal to the brain that this is a glass of water, right? Your brain has to do what? Interpret that picture, right? So sensory input is going from the retina of the eye to the brain. Now brain is doing integration, interpretation. Now you tell me, just for fun, in this case, what kind of interpretation your brain will do? First thing brain will think, is it water or acid? Right? Then if your brain thinks it is water, all these things must happen very fast. Thinks water, then it will think, is it clean or dirty, right? Should I drink it or not, right? All these interpretations must be done by the brain, right? Not only then, before brain sends signal to the muscles of the hand to move the hand to grab the glass, right? Brain has to do, you see here, many other things. What's the distance, right? What's the shape of that glass, because you have to grab it, right? Move the fingers. So all those things are done by the brain, right? That's the integration, very complex, lot of things. Then brain sends signal to the muscles, in this case, again to the muscle, right? To get the glass of water. So brain is sending motor command to the muscle. So you see, both examples are showing you that sensory input going from the receptors to the brain. Brain is interpreting, analyzing, right? And sending motor command to the organ to perform the task or action. So I can give you many examples, just those two I believe is got clear idea. So here you see the blue part is the sensory input from the, in this case, retinal receptor, visual receptor to the brain, and then integration in the brain, the green, and then motor output is the red part to the muscle. Now the division of the nervous system. We divide the entire nervous system into two parts. So nervous system is first divided into two divisions or two branches: central nervous system or CNS and peripheral nervous system or PNS. Central nervous system consists of the brain. How many brain? One, right? And the spinal cord. How many? Also only one. So, one brain and one spinal cord forms the central nervous system. So, central nervous system consists of a brain and a spinal cord. Peripheral nervous system consists of the nerves. Okay. Now, the nerves could be two types: afferent and efferent. Okay, afferent and efferent. So what's the difference between afferent and efferent? This is your brain, this is the spinal cord. Okay, so what happens, many nerves are attached to the brain, and so these are the nerves attached to the brain, and many nerves are attached to the spinal cord, both sides of the spinal cord. Okay. So first, those nerves are attached to the brain. Those are called the cranial nerves, because this is the cranial part, right? Head is the cranial. So those nerves are attached to the brain. Those are called what? Cranial nerves. Cranial nerves. You have total 11 pairs. Sorry, 12 pairs of cranial nerves in human. 12 pairs of cranial nerves. And those nerves are attached to the spinal cord. Those are called the spinal nerves. Very simple, right? Spinal nerves are attached to the spinal cord. Cranial nerves are attached to the what? Brain. Okay. Now, these nerves, some of these nerves take the signal towards the central nervous system, and some nerves take the signal away or out from the central nervous system, opposite direction. You already know, you remember I gave you the example. If something hot touches your skin, the signal should go from the skin to the where? Brain, right? So this signal is going towards the brain. Make sense? So you need nerve to take the signal towards the brain, right? Now after interpretation, then brain sends signal to the muscle, right? So the nerve taking the signal from the brain to the muscle in opposite direction, right? So one is taking this way, another is taking that way, right? So now you know that you need sensory input, motor output, right? So those nerves take the signal towards the brain. Those are sensory or motor? Sensory, right? And those are taking out, motor. So this is sensory. This is what? Motor. Sensory input, motor output. So you need both types, right? So some nerves will take the signal towards the brain, to the brain. Some nerves will take the motor command out from the brain. That's why you have two types of nerves. Sensory nerves are called afferent. So afferent are sensory sensory, and efferent are what? Motor. So this one is sensory, taking the signal to the brain. This one is motor, taking the signal out of the brain. Afferent, remember, arriving, and efferent, exit. If you just remember that, will make it clear, easier. Afferent, getting in, efferent, getting out, exit from the brain. Is it clear? So sensory and motor, or afferent and efferent. That's how we divide the nerves. Okay. So you see, we divide the nerves here in two ways. One is by looking at the attachment, right? Those are attached to the brain, those are called what? Cranial. Those are attached to the spinal cord, those are spinal. That is structural. Another is functional. Which way, right? The signal is being carried. Sensory or afferent, motor or efferent. This is the functional division. Okay. Now motor could be two types. Voluntary and involuntary. Let me give you a simple example. If something hot touches your skin, okay, against an example, or let me give you another simple example. You are thirsty, you will drink water, so you will send your hand to the glass, right? Is that voluntary or involuntary? Voluntary. If you decide, no, I want to move, you can do that, right? You are making decision and then sending hand to the glass, right? So it is voluntary. It is listening to your command, right? Now, if I hit the patellar ligament here, leg shoots forward, right? Even if you think you want, it will happen, right? So it is involuntary. So you see that the motor could be what? Voluntary, that you are grabbing the glass, right, to drink water. Involuntary, reflex. So that's why you have two types of nerves. One is for voluntary, another is for involuntary. Now if I ask which one is called autonomic, voluntary or involuntary? Involuntary is autonomic, right? It will not listen to you. You are not controlling. So involuntary is also called autonomic. Autonomic division of the motor nerves. So involuntary is autonomic signal. Okay. How many spinal nerves we have in human body? We have 31 pairs. Cranial nerves we have 12 pairs, and spinal nerve we have 31 pairs arise from the spinal cord. Okay. Now, the autonomic has two divisions. The autonomic is divided into two, sympathetic and parasympathetic. Sorry, I'm right here. I'll write here too. Sympathetic division of autonomic and parasympathetic division of autonomic. Okay, so autonomic is divided into autonomic nervous system. It is motor, one type of motor is divided into sympathetic division and parasympathetic division. Okay. sympathetic activation occurs when the body is in excited condition. So, if sympathetic activation occurs, your body is like in excited condition. You know, when you watch a movie that has a lot of excitement, okay, you are watching a movie that has a lot of excitement. Which division will be activated? Sympathetic. When you are in relaxed condition, you are relaxed, sitting on a couch, you know, watching nice pictures. So that is the activation of parasympathetic. Okay. So sympathetic activation increases the heart rate, makes sense, because excitement. Increases the muscle tone. Increases the second respiratory rate will be increased, okay, and the pupil dilates. Dilatation of the pupil. Parasympathetic activation does opposite. Decreases the heart rate, decreases the blood pressure, decreases the respiratory rate, and constricts the pupil. So just opposite. Keep the blood pressure, right? Parasympathetic, relaxed condition. What are the changes occur when you are in relaxed condition? Blood pressure goes down, heart rate goes down, right? Pupil constricts. Now, that's how we divide the nervous system. This is a nice chart that is showing exactly what I explained to you. First, we divide the entire nervous system into the central nervous system and peripheral nervous system. So you see the top, CNS and PNS. Central nervous system consists of how many structures? Central nervous system, that's the cranial nerve. One brain and one spinal cord, right? And peripheral nervous system consists of nerves, right? We have many nerves. Now, those nerves are attached to the brain. Those are called what? Cranial nerves. How many? 7. Those are attached to the spinal cord. Spinal nerves. How many? 31 pairs. Right? Now, functionally, we divide those nerves into 2 types. Sensory, motor. Sensory takes the signal to the brain. Motor, command, goes out. Right? Okay. So now, motor could be how many types? Voluntary and involuntary. Or voluntary and autonomic, right? Autonomic is divided into what? How many divisions? Sympathetic and parasympathetic. Okay. So now sensory is also called afferent. Motor is also called efferent. Exit. Right? Arriving and exit. Is it clear? Kind of, right? Okay. Okay, now another thing. The term somatic and visceral. Very simple. The word somatic means the outer structures of the body. For example, your skin, muscles, skeletal muscles, okay, joints. Those structures are called somatic. outer structures. Visceral indicates the internal organs. Internal organs of the body. Liver, kidney, right? Spleen. Those are internal body organs. Skin, muscle, joints, those are outer structures of the body, right? So somatic and visceral. We also use the term somatic motor and visceral motor. Somatic sensory, visceral sensory. The nerve is going where? That's the reason we divide. Now you tell me, if I send the signal from the brain to the muscle, right? That motor, right? Going from the brain to the muscle, motor. Is that somatic motor or visceral motor? Somatic. Is it clear? Because muscle belongs to somatic, right? Skeletal muscle. If a signal goes from the brain to the stomach to secrete the gastric acid, okay, that is visceral. Is it clear? So that's the difference. The somatic motor, visceral motor. Somatic sensory, visceral sensory. Now let me give you the sensory. You are having pain in the muscle. Pain signal goes from the muscle to the brain, right? Pain in the muscle. So it will go from the muscle to the brain. Or something bites you. That pain going from the skin or muscle to the brain. So that is sensory, right? Sensory. Is that somatic sensory or motor sensory, visceral sensory? Somatic sensory, because from the skin or muscle, right? Now you got ulcer in your stomach. Pain is going from the stomach wall to the brain. That sensory is somatic or visceral? Visceral. From the stomach pain, right? Stomach ulcer, pain is going to the brain. Is it clear? Is it clear? Okay. So you see, both motor and sensory could be somatic or visceral. Okay. The types of cells in the nervous system or neural tissue. Two types of cells are present. Supporting cells are called the neuroglial cells and the main cells are called the neurons. First, what are the functions of the neurons, the main cells? If I ask you, very simple answer: generation and transmission of electrical signal. Production and transmission of what? Electrical signal. That's the function of the neuron. Neurons perform their functions by producing and transmitting the electrical signal. And that signal will then release the neurotransmitters. That's the different. Neuroglial cells, the supporting cells, are very important too. Many important functions of supporting cells have been identified so far. Probably more are coming. A lot of research are going on. So far, we know that neuroglial cells perform following important functions. Help to migrate, some neuroglial cells can migrate towards the site of injury. If any injury occurs in the nervous system, neuroglial cells can move towards that site of inflammation or injury. Why they need to move? Because they can engulf the microorganisms or dead cells. That's why they will move there and will remove the microorganisms or dead cells by phagocytosis. So that is another important function. Not only they move towards the site of inflammation or injury, they do phagocytosis. engulf. Some neuroglial cells guide the young neurons, newly formed neurons, to move towards a certain area. You all know that when the brain is formed, the neurons multiply. So, small neural tissues here, so the neurons will multiply to produce more neurons, and the neurons will move towards different directions. For example, this will form one part of the brain, this will form another part of the brain, this will form another part of the brain. So, which one will go to which direction? That is guided by the surrounding neuroglial cells. Okay, so that is another interesting finding, that neuroglial cells, the presence of neuroglial cells guides the movement of the neurons. The research has shown that if you inactivate those neuroglial cells in that area, the movement will not occur. The neurons will not move. Control the chemical environment. You know that neurochemicals are present in the brain, and sometimes the depletion of neurochemical can occur. So in that case, the neuroglial cells will produce the neurochemicals to bring the level up. So regulating the neurochemicals is another important function of neuroglial cells. Insulation, another very important function. Some neuroglial cells cover the nerves. So that is the insulation, electrical wires in your house, right? All electrical wires are covered, right? Insulated by covering. So neuroglial cells cover the nerve fibers or axons. Why that is important? Electrical signal, right? So nerves, or the axons transmit electrical signal, right? If you cover the nerves, the transmission will be efficient, faster, and loss of transmission will not occur. Make sense? Otherwise, electrical signal will get lost. So to prevent the loss of electrical signal and better transmission, must be insulated or covered. Otherwise, you have many nerves in your body, right? If they are not covered, from the nerve the electrical signal will quickly enter into the muscles, right? To other structures, spread, right? Sideways, and will go to other structures that you don't need. Electrical signal should only go to the particular structure. So those are some important functions of neuroglial cells or supporting cells. Now, many different neuroglial cells have been found so far. The important ones are, you need to remember these names: astrocytes, microglia, ependymal cells, oligodendrocytes, satellite cells, and Schwann cells. These are few very important neuroglial cells. Now, in next few slides, what I will do, I will go over these neuroglial cells and will mention just one or two important things about each of these. You have to remember that. Make sense? Okay. Astrocytes look like stars. That's why they are called astrocytes. You know astronomy, right? Study of a star. So astrocytes look like stars. Astrocytes are most abundant type neuroglial cells, most common type neuroglial cells. And astrocytes perform a very important function. What is that? It forms a layer around the capillaries of your brain. It forms what? A layer. Where? Around the capillaries of your brain. That is important. Extra layer around the capillaries of your brain. And that is called the blood-brain barrier. You see here, this is your brain, and inside the brain you have capillaries. So this is a capillary, just I'm showing one capillary, and astrocytes. For example, this is an astrocyte. It sends a process to the capillary wall, and that process covers the capillary wall. This is another astrocyte, okay? Sends a process. Those are called foot processes, leg processes, and that cover the capillary. Okay? Make sense? So that extra layer is the blood-brain barrier, because we know inside the capillary we have blood, right? Blood is here. And you have the neurons here. Brain tissue is around the capillary. So, in case of your brain, the capillary has an additional layer, not in other capillaries of the body, only where? In the brain capillary, right? So, the toxic chemicals, you know that blood always contains the toxic chemicals. The toxic chemicals will not be able to enter into the brain tissue. Extra layer, right? So, the harmful toxic chemicals will be prevented from getting out, will not be allowed to get out. Brain tissue is the most sensitive tissue, you know, right? Highly sensitive. So, toxic chemicals should not enter into the brain tissue. So, very important function. So, three things I have mentioned here. It looks like what? Star. This is the most common type, and it forms what? Blood-brain barrier layer around the capillaries. Microglia or microglial cells. These cells have long processes, and these cells do phagocytosis, engulf the microorganisms or dead cells. So, microglia provides defensive function, right? Destroy the microorganisms and also removes the dead cells from the site of inflammation. Ependymal cells. These cells are present in the ventricles. Now the question is, what are the ventricles? Inside the brain, remember, you have cavities. For example, you have the largest cavity is called the lateral ventricle. Lateral ventricle. So, ventricles are the cavities filled with fluid called cerebrospinal fluid, CSF. So, this is a ventricle inside the brain. The ependymal cells line the wall of the ventricles. So these are the ependymal cells. And the ependymal cells have cilia, soft hair-like structures like this. Okay? So cilia, soft hair-like structures are present in the ependymal cells, and they line the wall of the ventricle. And the movement of cilia moves the cerebrospinal fluid inside the ventricle. Make sense? So inside the ventricle you have cerebrospinal fluid and the cilia are always moving, right? So that helps to move the cerebrospinal fluid, and cerebrospinal fluid must get out, circulate around the brain and the spinal cord. In subarachnoid space, you'll learn that later. Just know that the fluid should get out and circulate around the brain and the spinal cord. So that movement is important to push the fluid. Movement of the fluid and pushing the fluid out, circulate, creating current flow of the fluid. Okay. Now, insulation, another important function. Insulation is given by three types of neuroglial cells. First, one type is oligodendrocyte. Oligodendrocytes form the covering of many layers. You see here the yellow structures are the nerves, and around the nerves you see many layers are formed by the oligodendrocyte. This is the cell body of oligodendrocyte, this round one, like a round moon or full moon, and from the cell body you see the processes come out and they form the sheet around the nerve fibers, and sometimes they form many layers and that kind of insulation by oligodendrocytes are given around the nerves in the central nervous system, that means in the brain and the spinal cord, not in peripheral nervous system. So oligodendrocytes form the sheet called the myelin sheet around the nerve fibers in the central nervous system. We have to remember that, central nervous system. Now, in the peripheral nervous system, there are two types of neuroglial cells. They form insulation. Satellite cells form insulation around the cell body of the neuron. The yellow structure is the neuron. So around the cell body, the satellite cells form insulation, and around the axon, Schwann cells form the insulation. Okay. So you see here, around the cell body here, these are the satellite cells, and around the axon, these are the Schwann cells. Okay. In the peripheral nervous system, these two types of neuroglial cells give insulation. So I may ask you that which one form insulation around the cell body of peripheral neuron, satellite cells, right? Which one forms insulation in the axon of peripheral neurons, Schwann cells? Which one forms insulation around the nerve fiber in the central nervous system, many layers? That's the oligodendrocyte. So that's about the neuroglial cells, supporting cells. Now we'll see the main cells. Those are the neurons. Neurons are different than the other cells of your body. Quite different. How they are different? Because they have some special characteristics. Make sense? They are different. What are those special characteristics the neurons have? Neurons are long-lived. They can stay alive for 100 years or longer. But remember, neurons, although are long-lived, but there is a condition. If you don't bother them, okay, if you don't disturb them. Opposite is true too. Neurons are most sensitive cells of the body. Most what? Sensitive cells of the body can quickly die if you bother them. You know that if you open the skull and leave the brain tissue exposed to the air, the brain tissue will start to deteriorate. So sensitive, highly sensitive. So if you don't bother them, continuously give them oxygen and nutrition, they will stay alive 100 years or more. If you bother them, they may quickly die, easily die. So highly sensitive neurons, cells. And mitotic, that means A means absence, remember. A means absence. So amitotic means absence of mitosis. Mitosis is what? One type of cell division. So mitosis usually does not occur in mature neurons. Once neurons get matured, no mitosis or cell division usually occurs. There are very few exceptions, but usually or normally amitotic. And that is a problem, right? If the brain tissue dies, no new brain tissue will be formed. Sometimes stroke, right? That destroys the tissue. And the person suffers rest of the life, right? Without very little improvement. So, once the brain tissue dies, no new cells are regenerated. Usually, I said there are exceptions. Depend on continuous supply of oxygen and glucose. You all know that. If I stop the blood circulation to the brain in few minutes, the person will pass away, die, right? So, continuously your neural tissue or neurons need oxygen and glucose. If I stop circulation to my hand, like blocking the arteries here, right? The muscle tissue will still stay alive for long time, will not die. If I stop circulation to your brain, blocking the arteries here, what will happen? You will get unconscious, right? So you now know that continuous blood circulation, that means the nutrition and oxygen are needed. And neurons, I have mentioned, generates and transmits electrical signal. So that is another important characteristic of neurons. They can produce and transmit electrical signal that can travel far away. Parts of a neuron. A typical neuron has a cell body and processes. So this is the cell body. Contains a nucleus, and in the cytoplasm you have granules. These are called niso granules or nisal bodies. Okay, same thing. These are highly concentrated chemical particles. Okay, nisal granules or nisal body. That is the cell body, and you have processes. From one side of the cell body, you will see multiple short branching processes. These are called dendrites. Multiple short and have branches. From the opposite side, a single long process arises, and that is called the axon. And the area of the cell body from where the axon arises, that is called the axon hillock. Axon hillock is the area from where the axon arises in the cell body. The end of the axon is called what? I mentioned when I talk about the neuromuscular junction. Axon terminal, right? The end of the axon is called terminal, end, axon terminal. And at the terminal, you have button-like structures. Those are called terminal buttons. Now, around the axon, you have the Schwann cells. They form insulation. You must remember a few minutes ago I mentioned. Around the axon of peripheral neurons, you have Schwann cells. Is that right? Okay, myelin sheath. Okay. So Schwann cells form myelin sheath around the axon. Now, you see that in between the Schwann cells, you have the spots that are not covered by the myelin sheath. So these open spots are called nodes of Ranviers. These uncovered spots are called nodes of Ranviers. Okay, and now always remember, this is very important, which way the electrical signal is transmitted. The dendrites always bring the signal into the cell body. So dendrites bring the signal into the cell body, and after the cell body processes that signal, axon takes the signal out or away from the cell body. This is always true, unidirectional transmission. Okay. Now, in the neural tissue, what happens? The axons give signal to the dendrites of the next neuron. So again, you see this is the next neuron. These are the dendrites. They receive the signal from axon terminal here. So the neurotransmitters are released here from the axon terminal. You remember, in case of neuromuscular, axon ends of the muscle fiber. But in the brain or neural tissue, axon ends on the dendrite of next neuron and release the neurotransmitter here. And this is the synapse. So at the synapse, you'll see axon terminal ends on the dendrite. The dendrite receives the signal and brings it to the cell body, and cell body then again sends the signal out to the axon, and you have another neuron here. Okay? So these dendrites will receive the signal again. So always this way. Okay? Neuron to neuron, from one neuron to the next neuron. From the axon terminal of previous neuron, the dendrites of the next neuron receive the signal. But they are not physically attached. There is a tiny space or gap. That's the area where the neurotransmitters are released. Make sense? Yes.
Can you also call a button? Is there another name for that?
Neurochemicals, neurotransmitters. Do you know any other name?
Is there another name or is that?
Synaptic knobs or synaptic buttons. Same thing. Knobs. But neurochemicals are neurotransmitters. There are two types of neurotransmitters: excitatory and inhibitory. Just know that much. Two types of neurotransmitters: excitatory and what? inhibitory. Okay. Now I can talk the whole day about the neurotransmitters because I teach neuroscience at WashU, and that is only neuroscience, right? The whole semester. So I don't want to go into detail. Just know that two types of neurotransmitters: excitatory, inhibitory. For example, GABA. Have you heard that? GABA. GABA is an inhibitory neurotransmitter. So what will happen if GABA is released here? Then signal will be blocked here, right? Will be slowed down because it is inhibitory. Will slow the signal, inhibit the signal. Excitatory, glutamate, dopamine will excite, so signal will go faster, right? So you have both types of neurotransmitters, and that regulates the transmission of signal at the synapses. Make sense? At the synapses. How fast the signal will go, or should it be blocked or regulated? Okay. Inside the central nervous system, we see some structure. We see the white matter, gray matter, tracts, nuclei. So just know what are those things. So this is the brain. Okay, so this is the brain, and the outer part of the brain is the gray matter. Looks gray. So very easy, even without microscope, you can cut the brain and see inside, and you will see clearly the outer gray and inner white part. So this part is the gray part called the gray matter, and the inner part is the white matter. Now the question is, why the outer part is gray, inner part is white? Very simple. The cell bodies and dendrites are located in the gray matter. And why this area looks gray? Because you know that inside the cell body you have the Nissl granules. I just showed you a few minutes ago. In the cytoplasm you have the concentrated chemicals, Nissl granules. So all these cell bodies have Nissl granules, and that gives the color of this part gray. Now let's see this part, white matter. Why it is white? Because the axons are covered by myelin sheath, which is a glycolipid, whitish layer. So all these axons are covered by whitish myelin sheath. That's why this area looks white. Make sense? Because all axons are there in this area, so it looks white. So where you have the cell bodies, that area looks what? Where you have the cell bodies? Gray, right? Because of Nissl granules. Where you have the myelinated fibers? White, because the myelin sheath is whitish color. So that is gray matter, white matter. Now, the tracts and nuclei, two other things you very often see inside the central nervous system. Tracts and nuclei. Kind of similar to gray matter and white matter. The difference is in certain areas inside the central nervous system. For example, here you have many cell bodies heavily packed. Here is less heavily packed in gray matter, but in certain areas the nuclei are more densely packed. and this area will look gray but darker gray, and that is called the nuclei. So you will see nuclei. Now, in certain part of the central nervous system, you have the fibers, axons, but heavily packed, densely packed. For example, this is another nuclei, heavily packed cell bodies, and they are connected by these fibers. These fibers are densely packed. So this is the tract. Okay, so tract is the bundle of fibers, and nuclei are the densely packed cell bodies. Densely packed cell bodies, and tract is the densely packed fibers. So when you cut the band, you can clearly see these structures. Okay, so you can clearly see those. Okay. Now, that's all those are in the central nervous system: gray matter, white matter, tract, nuclei. Now, in the peripheral nervous system, in nerves, you know, the cranial nerves, spinal nerves, you have nerves. Nerves are formed by, if you see the fibers are bundled together, like these are the cell bodies of neurons, and these are the fibers are bundled together in peripheral nervous system, that is called a nerve. So no nerve in the central nervous system. Nerves are only the peripheral nervous system, but nerves are very similar to the tracts. The bundle of fibers in the central nervous system are called the tracts. Bundle of fibers in the peripheral nervous system are called the nerves. So in a nerve, you have many axons. Make sense? Okay. Now, cluster of neurons in peripheral nervous system is called ganglion, not nuclei. So in this case, ganglion. So where exactly same thing. This is peripheral nervous system. This is central nervous system. In central nervous system, it is called nucleus. In peripheral nervous system, it is called ganglion. In central nervous system, this is called tract, the bundle of fibers. In peripheral nervous system, bundle of fibers from the nerve. So nerve and ganglion are in peripheral nervous system, nuclei and tracts in the central nervous system. But they are same. Structurally, they are same. Only the difference is where they are located, in CNS or PNS. Structural classification of neurons. By looking at the processes, we divide the neurons into three types. Most common type, the typical neurons, are multipolar, that I did draw on the board, and you see in the pictures. When you see a picture of a neuron, you see multipolar. That's the most common type, typical neuron. So this is the cell body, one long axon, multiple short branching processes. So that's the multipolar. Now, if you see, the neuron has one axon and only one dendrite. So this is called bipolar, two processes. So this is bipolar. If you see, the neuron has only one axon. This is the cell body, no dendrite. But the axon could be like this. The cell body is attached to the side of the axon, and this is actually only one axon. These are the ends of that axon. And in this case, we will say unipolar type. Okay. So, sometimes called pseudo-unipolar. The reason is, you may think two processes, but actually only one axon is here. No dendrite. No dendrite, only one axon. But since the cell body is attached somewhere, in the middle, you may think one is axon, one is dendrite, but that is false. Pseudo. Synapse are also known as chemical synapse. Why? Because neurotransmitters are released at the synapse I have explained. Now, the synapse could be two types. You already know both. One, when you have learned the neuromuscular junction, that is one synapse. That means what? This is the neuron, the axon terminal. This is the muscle fiber. So this synapse is neuron to muscle, neuromuscular junction. The axon terminal meets the muscle fiber. That is one type of synapse. And another type of synapse that I did draw a few minutes ago, axon terminal, neuron to neuron. This is next neuron. So the dendrites, this is the signal from axon terminal. So this is the neuron to neuron synapse. Okay. In both cases, neurotransmitters are released here. In this case, it is ACH. You already know that. In this case, could be any excitatory inhibitor. So these are the two types of synapse, right? Neuron to muscle, neuron to neuron. Very simple. Both are chemical. Last thing, the reflex. The reflexes are rapid, autonomic responses to stimuli in which a particular stimulus always causes the same response. So here, this is the definition of a reflex. Now, three things are important in this definition. To be a reflex, three conditions must met. How many? Three. To be a reflex, it must be rapid, must be autonomic, that means involuntary, right? You cannot do it. It should happen by itself. And must be repeatedly occurring. Repeat the same thing. If you present the stimulus 10 times, it should show the same response, not opposite response, right? Same response every time. Is it clear? So three conditions. What are those? Must be rapid, autonomic, and repeatedly occurring same response, right? Now let me give you an example of a reflex. If I put bright flashlight on your eye, pupil, you know, the opening pupil constricts, right? To limit that entrance of light, right? Pupil constrict. That happens. You know that, right? Put flashlight on the eye, pupil will constrict. Immediately. Fast, right? That is number one. Rapid. Number two, autonomic. You don't do that, right? Pupil constricts by itself. You even don't know. If you look at flashlight, pupil constrict, even if you don't know, right? It will happen. So autonomic. Number three, if I present 10 times flashlight on your eye, 10 times your pupil will do what? Constrict. It will not do opposite. Every time it will do the same response. Is it clear? So it should happen every time, repeatedly. So those are the three conditions. Now the reflex arc is the complete pathway of reflex. To occur a reflex, the pathway, the complete pathway is called the reflex arc. So, what are the components of reflex arc? 5 components. Receptors must be stimulated by the stimulus. Sensory input, you already know, sensory neurons will take the signal towards the central nervous system. Integration will be done in the brain or the central nervous system. that is the interpretation. Motor output will be done by motor neurons and effector will perform the action. Clear? Let me give you another example. You know, a very common reflex is here. Knee jerk, knee reflex, right? So what you do? You hit the patellar ligament here, right? When you hit, the ligament has the receptors, stretch receptors, okay? So you are activating the receptors, make sense? So that receptors sending signal where? To the spinal cord, central nervous system, right? So motor neurons. And then after integration, the signal will go back. In this case, signal will go back to the muscle, leg muscle, right? So muscles are the effectors. Remember, so receptors and effectors are two different things, right? Receptors are getting activated by the stimulus, but effectors are performing the actions. So two different things. Okay. But for to be reflex, it must be, I don't know. Okay. Okay.